pieces. Jason, we'll get you to do this. Do you think you could get one of these pieces out of the operation game without touching the sides?
I hope so. I'm going to think positively. I'm going to go for an easy one.
Positively on a circuit.
Whoa, positive on the circuit. Not being negative.
Okay, good.
There's no bad.
Now, I wonder what would have happened if he would have touched the side. So if you would have touched the side, let's see.
Ooh.
Okay, so the nose is lighting up, and we can hear it's vibrating. It's making a noise. Why do you think that it's doing that? Any ideas?
Science?
Right, it is science. So, because these are metal, when you touch the side, it's actually making a circuit. Now, if you look here, I have a model of a circuit. So this is our battery, our wires, and our light. If you look inside the wires, you'll see glitter. Wow, that's not actually glitter. What that is those are electrons. Now, everything in the whole world is made up of tiny little building block pieces called atoms, just like this atom that I have here. Now, in the atom, in the middle is a nucleus, which is like the core, kind of like when you eat an apple, you have an apple core, it's kind of the same thing. Now what the nucleus is made up of is protons, which carry a positive electrical charge, and neutrons, which carry no charge at all. And what circles around the outside is electrons, and electrons, they carry a negative charge. So when they're introduced to energy, they start to go crazy and they move around. And they actually travel from the battery through the wires to bring us light or to make things work by creating electricity. Now, a circuit is a path in which an electric current runs through a power source like a battery and through components like a light bulb. An electric current is the movement of electrons, like I said, through the wire. But they can only move through a wire, like a copper wire, because it's a conductor. If our wires, or if we had something in our circuit that didn't allow the electrons to move through it, then that would be called an insulator. So there are a few parts of every circuit. One is a power source, so we have a battery here, and that's where the energy comes from that causes the electrons to start to move. Then we have a conducting path, which is our wires, where the electrons move through and bring the electricity to the load. The light, or whatever you're trying to power, is what your load is. So in this circuit, it would be a light. Now, using this model, we can look at it. What happens with the electrons is that when it comes out of the battery, that's the negative end of the battery. And it always goes in to the positive end of the battery. Now, if we were to cut this wire, it would become an open circuit, and then it wouldn't work because the electrons wouldn't be able to make it to the load. But because this is closed and it's just a continuous circle, it is then called a closed circuit. So there's a couple kinds of circuits that we can have. On here, you can see there's a series circuit, which is just one, where there's one path for the electrical flow to go through, the electrical current. And then you can also have parallel circuits. And the parallel circuits actually have a couple of loops, and they can be two or even more. So you can have pretty large circuits. So what are some examples of places where we would find circuits in our day-to-day life? Anybody think of any?
A light switch.
A light switch, right? The lights, that's electricity. Anything else?
Like maybe in a small appliance, like a blender or a toaster, I don't know.
Absolutely, yeah, we need power to make those things work. And actually when there's electricity, it actually causes things to heat up. So that's how your toaster makes toast for you. So now that we've learned a little bit about circuits, let's look at some circuits in action.
Okay, so we're gonna start out with a Play-Doh circuit. So right here we have the battery pack, so we're gonna insert the batteries, and you can see it's all labeled here, so the negative side goes in where the negative is, and then the positive into the positive side. So let's just get those in there. And then we are going to connect the Play-Doh. So I have 2 bits of Play-Doh here, and these are conductors. So let's put the positive into the one side of the Play-Doh. We'll put the negative into the other side of the Play-Doh. Now it's a little bright in here, so it might be hard to see, but when we stick this light in here, it should go on. Oh no, it's not working. Does anyone know why it's not working? They want to find the closest path. So if we separate the Play-Doh, oh, now the light's turned on. I know it's really hard to see, but it's on. Okay, there we go. So that is now completing the circuit. But if the Play-Doh touches, then it will turn off. So that is a Play-Doh circuit.
All right. So instead of using Play-Doh, I found a lemon. And the premise of this lemon is to make a battery out of it. And so it's essentially a wet cell. And it's a wet cell because when we suspend two metals in an acid, we can create a current. So we have a zinc nail. I'll use this lemon instead. So our zinc nail, which is our negative end of our battery, and a penny plated in copper, which is our positive. So we take our alligator clips and we connect them to the lemon, positive and negative. And then we also use an LED to show how we can get a current. And these are special because you have to connect them properly. So there's a negative side and a positive side, and you can tell by either how the length of the two legs coming out, the shorter one's the negative, or there's also around the edge, it's flat. So you can, and that's the negative side. So you always want to hook up your cell properly, so the positive goes to the negative end, negative goes to the positive. Now, this does not light up, and that is because lemons aren't the best battery to use for everything. They're not very strong, so you will need to connect more lemons in order to get a faint light out of this.
Awesome. Well, electricity also has the ability to work with magnetism to create motors, things that move. Magnetism is in so many different things, and electricity actually creates its own form of magnetism. So when we use a battery, so for example, I have a D-cell battery here, and I've got some modeling clay just to stabilize it, and I have some electrical tape, which prevents electricity from getting transferred around. It's a nice weight, it's a not a conductor, an insulator, and some metal sewing needles, which will conduct electricity. If I put them on each pole of the battery, like so, I'm creating a basis for a little motor. Now I do have a magnet here, and if I place the magnet on top of the battery, what I should be able to do is take some wire that's coiled around, insert them into the needle heads, and give it a spin, and it'll continue to spin around and around until the battery runs out of power. And it does this because as electricity is flowing through the copper wire, it's creating a magnetic force around the coil, and that's interacting with the magnet that's on the battery, and it's essentially constantly attracting and repelling. Now, my experiments, I couldn't get this to work. I was wondering why. First, I tried using actual insulated wire. Well, this isn't strong enough to hold itself up, and I'm using too little of it. Then I found some nice copper wire, and I decided to use that. It's not working because it's not insulated. And so because it's not insulated, the magnet is just attracting. It's not,
Repelling?
It's not repelling, yes. So what is supposed to happen is it's supposed to be insulated copper wire, and only 1/2 of each side is supposed to be cut off. And that way, as it's spinning around, it's breaking the circuit just long enough to prevent the magnets from attracting each other. So by the time the circuit turns back on, it's turned enough so it repels, and it just keeps going until it runs out of power. Now, if I were to put the wires in here, it'll heat up, and I've made my fingers very hot in the last couple of days doing it. However, I do have a short demonstration of what this should look like, because I can't show you today because it's great. So if you just take a look up here, this is what it should look like.
This is what it will look like?
That's what it will look like. Yeah, exactly. It's what it should. It's what it will look like when everything gets ready. Now, if we use a stronger battery, or we use a bigger battery, or if we use stronger magnets, it should in theory, spin faster as there's a stronger magnetic force and more current flowing through the wire.
We also plan on having a couple of tables set up so that we will have our own, like, build your own circuit, like create your own circuit. So in there, we want to have some different materials for them, such as alligator clips, batteries and battery cases, some more lights, and we're also considering maybe incorporating some snap circuits as well. And so, yeah, so this is our presentation, and we called it Running Around in Circuits.